Greetings to all my tech heads out there in the KevTechify nation, and if you're new here, welcome. In this episode, we're going to look at binary number systems. We'll be discussing binary and IPv4 addresses, binary positional notation. We're going to look at converting binary to decimal, and then decimal to binary, and then finally we're going to come back and talk about IPv4 addresses again. This episode is part of my series on Introduction to Networks. I'm Kevin here at KevTechify. Let's get this adventure started. Binary number systems and IP addresses, they are related. When we talk about binary is only having two values, and the two values when we talk about computers and networking are ones and zeros. So a binary system only has two values. It's a 1 and a 0. Decimal systems, the number we're used to that we learned since kindergarten on up, consists of 10 digits, 0 through 9. And then we have repeating combinations to give us bigger numbers than 0 through 9. As we look at these IP addresses, they use the binary number system. Binary number systems, when you look at the actual number itself, it contains the one of the two values, the 1 or the 0. Each 1 or 0 is called a bit. When we look at an IPv4 address, it is 32 bits long. So it's a string of 32 ones or zeros. And then we take those 32 ones or zeros and we break them up into octets. So 8 groups of bits, 8 groups of bits, 8 groups of bits, 8 groups of bits. We break those up to help us as humans understand that. But the computer itself, they only understand the string of 32 ones and zeros. And when you take 8 bits and you put them together, that's called a byte. So 1 or 0, one value, that is 1 bit. When you take 8 of those bits together, that is called a byte. And when we're talking IP addresses, those 8 bits represent an octet. And so an IPv4 address that's 32 bits long, it has 4 octets. 4 octets, 4 times 8 gives us 32. That is our 32 bits. Now, instead of looking at 8 ones or zeros in each octet, what we do for humans to make it a little bit easier is we take that 8 ones or zeros and binary, and then we convert it into decimal to give us a number between 0 and 255. Much easier to remember a number of 192 than it is to remember 8 ones or zeros. The example would be 11001001. 192 is a lot easier to remember of that. When we see IP addresses, like these examples here, we see 209.165.200.225. That is an IPv4 address. Down here, 192.168.10.1, 192.168.11.1. Those are all IP addresses. Now, we've converted them into octets, and we've changed those octets into numbers we can understand. But we do have to remember that when the computer sees an IP address, this is what the computer sees. They see a string of 32 ones and zeros. So this represents the IP address that was here. This represents the 192.168.10.1 address. This over here represents 192.168.11.1 address. Now, this graphic is a little bit off. The computer itself, it sees the string of 32 ones and zeros. There are no decimals in breaking up that string of 32 ones and zeros. Once again, that is done for just humans, so we can more easily identify where the octets are, those groups of 8 numbers. We're going to start looking at converting numbers between binary and decimal. We're going to start off with decimal because that's the system we're used to. That's the system that we've learned since kindergarten how to count. That's how we count dollar bills out to somebody. That is how we count really anything in this world. We count in a base 10 system. And so over here on the left side, we have this chart here. And what this chart is going to help us see the positional notation. And hopefully that'll make sense in a second. We'll start off on the left side with the blue. We have the Radix. What the radix is basically the base 10 system. That represents how many values we have. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 10 values because we got to remember we got to count 0 into there. Then this position number. What position is it? Is it the furthest right digit? Is this the second to the right, third to the right, fourth to the right? Notice the positions here, they start with 0. Because as we know, computers start counting with 0. The first value is typically assigned 0, and that represents the first value. So here, the first column is 0, second column is 1, third column is 2, fourth column is 3. In order to calculate the value of that column, what we do is we put the radix down here. So our base, how many possible values we have 0 through 9. We have a base 10 system, and then we put the position number right here. We then calculate that value out to give us this. Now, any number to the 0 power, that is a 1. Any number. Here we have 10 to the 0, so that is equal to 1. Then the next column over, we have 10 to the first power. Any number to the first power is that number itself. So we have 10 to the first power, that gives us 10. 10 to the second power. To the second power means the number times the number, so you do it twice. That gives us 10 times 10, that gives us 100. Here we take 10 times 10 times 10 3 times. 10 times 10 is 100, times 10 again, that gives us our 1,000. What this position value represents is the column. The first column on the right has the value of 1. The second column is the tens column. The next column is the hundreds column. The fourth column is the thousands column. This shouldn't be a surprise. Once again, this is the system we've learned since kindergarten. Looking at that. Now, the right side, the red chart over here, we have taken those values. And notice we have these values here. We have 1 in the first column, 10 in the second column, 100 in the third column, 1,000 in the fourth column. We then take a decimal number. Here, this example uses the decimal number of, uses the decimal number of 1234, 1,234. And so what we do is we take the value of the fourth column and put it right here. We take the value of this of the third column from the right, that's a 2. That goes in the hundredths. The value of the second column from the right is a 3. That goes over here. And the value of the column on the right, the ones column, goes over here. Now, in order to calculate this out, and once again, we've taken this for granted as we've done this all of our lives. But what we do over here, and we'll start in the ones column. We have the number, we have 4 that comes from over here from our decimal number. We take 4 and then multiply it by the positional value, which is 1. 4 times 1 gives us 4. Then we take the second number from the right, which is our 3 here. We take the 3 times the value of the column, the positional value of the column. So 3 times 10, that gives us a value of 30. We take the third number from the right, this is a 2, place it in the hundreds column. 2 times 100 gives us 200. And then in the fourth column from the right, the 1, we put a 1 in the thousands column. 1 times 1,000 gives us 1,000. At that point in time, then we go ahead and we add them up. So we have 1,000 plus 200 plus 30 plus 4. That gives us 1,234. Okay, this is a simple example. This simple example, now that we've laid this out, is going to help us when we go through and look at binary. But right now, what we're going to do is we're going to help show you how the system works, how we can lay it out a little bit longhand, go through the steps. We're going to break it down a little bit more. Once we have these steps, then we're going to go from a decimal system to a binary system. So right now, we're going to look at the decimal number 3,276. So I created this little chart. I put the values in there. We know these values. What I did was take the positional values of that. And how I got these positional values is I took the base number times number of the or to the power of the column they were in. And once again, remember we started at 0. So over here on the far right side, I have the base number of 10 to the 0 power. Once again, any number to the 0 power is 1. So that gives us our 1 at this point in time. The second column over, we have base 10 to the first power. Any number to the first power is that number itself. The value of this column then is 10. 10 to the second power, that once again 2 is the third value, 1, 2, or 0, 1, 2 in the third column, which gives us 10 times 10, which is equal to 100. That is the positional value of that one. 10 to the third is 10 times 10 times 10. 10 times 10 is 100 times 10 again. That gives us 1,000 here. 10 to the fourth is 10,000. 10 to the fifth is 100,000. And 10 to the sixth is 1 million. But our number was only 3,276. And notice how these columns line up for us. The positional value of this column is 1, and that's where our 6 is. That's the ones column. That's traditionally what we're not. The second column from the right is the tens column. Third column is the hundreds column. Fourth is the thousands column. We take that value. Now, once again, remember, this is base 10. This is a decimal system. Our values are 0 through 9, so we can have no other values than that. And now we go through the process of calculating it. We take the positional value times the number in here. So we have 1,000 times 3, that gives us 3,000. We move over to the third column from the right, and we have 100 in the positional value, 2 as the number. That gives us 2 times 100 gives us a value of 200. Then we move over to the second column from the right. That's the tens column, and we have a value of 7. We multiply it by the positional value of 10. That gives us 7 times 10, which is equal to 70. And then we take the far right column. We have a value of 6 times 1. That's a positional value. Once again, that's 10 to the 0. Any number to the 0 power is 1. That gives us 6 times 1, gives us 6. We now come over here and we add it up. We add up 3,000 plus 200 plus 70 plus 6. That gives us a total of 3,276. Once again, simple example. We're setting up the rules on how we come up with these values. We're going to take this, and then we can see, what if we want to make a change? What if we want to make a change? Let's say we want to change the value here in the fourth column. We want to change this value here from a 3, we change it to a 9. If we do that, then we have to come over to our calculations. We have to change this value to a 9. That gives us 9 times 1,000. 9 times 1,000 gives us 9,000. Add this up, 9,000 plus 200 plus 70 plus 6. That gives us a total of 9,276. We can change the values in here as long as those values are in our base system, 0 through 9. We can then change it and we can come up with the new number. Taking what we just talked about with the base 10 decimal system, we're going to look at the binary system, a base 2 system. Starting off here, our Radix, our base system here is base 2. We only have 2 values possible. We have a 0 or a 1. The positional number, we start at the right with a 0. First column is a 1. First column is a 0. Second column is a 1. 2, 3, 4, 5, 6, 7. There's a reason we're carrying this out to 8 places, because once again, remember, we have those octets. Those octets were 8 bits long, so we're going to carry these out to the 8th position. 8th position, starting with 0, that takes us up to 7. Then we go through and we figure out our calculation. Our calculation is our Radix, or our base number, to the positional number. 2 to the 0 power, any number to the 0 power is 1. So the value of this column is 1. Then we move on to the second column. 2 to the first power, any number to the first power is that number itself. 2 to the second power is 4. 2 to the third power is 8, 16. 2 to the 5th power is 32. 2 to the 6th power is 64. 2 to the 7th is 128. The easy way to remember this is starting at the right side. We start with the value of 1 in the first column, and then we double it. Times 2, that gives us 1 times 2, that gives, 1 times 2 gives us 2. Then we multiply that and we just double it again. That gives us our 4. Times 2, we double it. That gives us our 8. Double it again. 16, 32, 64, 128. That's the easy way to remember that. Once we figured out what our positional values are, come down to the red chart. Notice right here we have our positional values put into there. We're going to take the binary number 11000000, and what you can do is just take these 8 digits and put them right in here. Starting with typically you start on the right, so the first one was a 0, second number was a 0, third 0, fourth 0, fifth 0, sixth 0, seventh was a 1, that's over here, eighth is a 1, there. Now we calculate it out. And remember how we did that calculation. We did the number times the positional value. So we have the number right here, number 1, times the positional value. Positional value here is 128. We got that from going through our positional notation using our Radix and our position number. That gives us 128. Number 1 times 128, that gives us 128. 1 in the 7th column has a positional value of 64, so 1 times 64, that gives us 64. And then the rest of our number, if we look back here, are all zeros. Any number times 0 is 0. So we have 0 times our positional value of 32, 0 times 32 is 0, 0 times 16 is 0, 0 times 8 is 0, 0 times 4 is 0, 0 times 2 is 0, and finally we have 0 times 1 is 0 again. Once we have all these values here, all these calculated values, we add them up. Add up 128 plus 64 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0, or just easy, 128 plus 64 gives us a value of 192. That may have been a little complicated. I may have flown over a couple things. I'm going to show you, I'm going to break it down into some more steps, so hopefully we'll understand. If you like this episode on binary number systems and you get value out of it, and depending upon the platform you're using, please click that like button, give a 5-star rating, subscribe to my channel, leave a comment. Doing this supports the channel, which in turn helps me bring you more great content. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. We're going to take the system we just used when we talked about the decimals and calculating the values. We're going to take that system and then we're going to apply it to the binary base 2 system. Up on top, we go through and we figure out our Radix. Our Radix, once again, is the base number. So we have base 2, and notice we have all base 2s, and then we start with 0 in the first column, then 1 to the 2nd power, then to the 3rd power, 5th column is to the 4th power, 5th power, 6th power, and finally the 8th column is 2 to the 7th power. Go ahead, calculate that out. As you calculate that out, remember any number to the 0 power is 1, any number to the 1st power is that number itself, and then we have over here 2 to the 2nd power, which is equivalent to 2 times 2, that gives us 4. Next we have 2 to the 3rd power, which is 2 times 2 times 2. 2 times 2 gives us 4, times 2 again is 8. 2 to the 4th power is 16, 2 to the 5th power is 32, 2 to the 6th power is 64, 2 to the 7th power is 128. But I feel the easier way to remember that is if you start in the right column, you put 1, and then you double it. So 1 here, double that, that gives us a 2. Have a 2, double that, that gives us a 4 in the 3rd column. Take the 4, double it, that gives us an 8 here in the fourth column. Double it again, gives us 16. Double that gives us 32. Double that gives us 64. Double that gives us 128. What we're going to do is we're going to start and say, in decimal, we have the number 146. In decimal, we have the number 146. And what we're going to do is figure out what numbers we can add up using these calculated values here, this middle line in our blue chart. What calculated values here can we add up to get us to our 146? If we take 128, is that value over 146? No, that value is not over 146. So what we can do is we can put a 1 in that column. 128 plus 64, that gives us 192. 192 is over 146, so that's over our target. So we can't do that. We can't take a 64, and we go ahead and we put a 0 in there. Now, 128 plus 32, that gives us 160. 160 is over 146, so we've missed our target. We can't take that, so we put a 0 there in that sixth column. 128 plus 16, 128 plus 16 gives us 144. 144 is below that. We haven't overshot our target yet, so we can take a 128 and a 16. We're still not at 146, but we're getting closer. And we can put a 1 in that fifth column there. Through to the fourth, the 16's column. 128 plus 16, and our next number is 8. Add those together. 144 plus 8 gives us 152. Oh, we overshot 146, so we cannot use an 8. Go ahead and put a 0 in that column. Next value is 4. 128 plus 16 plus 4. 128 plus 16 is 144. Plus 4 is 148. We have overshot 146, but just by a little. So we cannot use the 4. We have to put a 0 in that column. Now, the next number available is 2. 128 plus 16 plus 2. 128 plus 16 gives us 144. Plus 2 is 146. There is our number. We can use that 2, so we go and put a 1 in there. We are at 146. Anything after that, we don't need to add any more on that. And so we can just put zeros in there. That gives us this number here. 1001010 is equal to 146. To prove it, let's go through and calculate our values to see if it actually does equal 146. And what we're going to do is we're going to take the value here of our number, our value here is 1, multiplied times the positional value, the value of the column, and then add those numbers all together. First one here gives us 1 times 128, that gives us 128. 0 times 64, that's 0. We're not even going to put it on the list. 0 times 32, once again, that's 0. We're not going to put it on the list. But then we're down here, we have a 1 times 16. 1 times 16 gives us 16. 0 times 8 gives us 0. Here. Then so we're not going to put that on the list. 0 times 4, 0. We're not going to put that on the list. But we do have a 1 times the positional value of 2. We'll go ahead and write that down. 1 times 2 equals 2. And then the column on the far right is 0 times 1. Any number times 0 gives us 0. So we're not even going to write that down. Go through, and now we're going to add them up. We're going to add up 128, 16, 2, and that will give us a total of 146. And what we just figured out is decimal 146, that's what we started with right here, is equal to binary is equal to binary 1001010. That's what we calculated right here. And then we proved it down here once again. Okay, that's one method to take a decimal number to a binary. I want to show you a little bit different method. I think it's easier, the method I'm going to show you next. The method, we're going to use the same number, but we're going to handle it a little bit differently. And the approach we're going to take is we have our number 146, and then we're going to start on the left side, the biggest number, the biggest positional value. Our number is 146. Can I take a 128 out of 46? Yes, it's more than 128, so I can subtract 128 out of that. I go ahead, put a 1 in the 128 column, and then I subtract it. 146 minus 128 gives us 18. Now, I put the 1 in the 128 column, I did my subtraction, and now I repeat the same questions again, but I use the value here of 18. Using the value of 18, can I take the positional value of 64 out of 18? No, 64 is bigger than 18. I cannot subtract that. What I have to do now is put a 0 in the 64 column. Go on to the next column, 32. Can I take a 32 out of 18? Nope, 32 is too big. We cannot take that out. Put another 0 here in the 32 column. Move on over here to the fifth column from the right. 16 is the positional value of that. Can I take a 16 out of 18? Yes, I can take 16 out of 18. First step I do is I put a 1 here in the 16 column, and then I subtract it out. 18 minus 16, that gives me 2. And then I start the process over with the value of 2, asking the question, can I take, from the next column, can I take a value of 8 out of 2? Nope, you can't, so I have to put a 0 in that column. Can I take a 4 out of 2? Nope, I can't do that, so I have to put a 0 in that column. Now, second column from the right, positional value is a 2. I am asking, can I take a 2 out of a 2? Yes, I can take a 2 out of a 2. That'll give me a 0, but I can still take that out. Now I go up, I put a 1 in the 2's column, and then I subtract my 2 out of 2 down here and gives me my 0. Once I have 0, I have nothing left to take out. So up here, for the rest of my numbers, now that I have a 0, now that I have a total of 0 down here on from the bottom right, bottom left, I can put zeros in there. And that gives me my binary number. And what we just did is decimal 146. That's what we are given here, is equal to 100,100,10. That is what the value we connected here. I feel this method is a little bit easier than the previous method. Starting with your number and asking, can I take the biggest value out of that? Yes, I can. We'll subtract those numbers, and then this is the number we ask that question with. Out of the next column, 64 column. Can I take a 64 out of 18? Nope, that gets a 0. Can I take a 32 out? Nope, that gets a 0. Can I take a 16 out of 18? Yes, I can. That gets a 1 here. We subtract it. Now we're down to a value of 2. Can I take 8 out of that? Nope. Can I take 4 out of 2? Nope. Can I take 2 out of 2? Yes, I can. That does give us 0 down here in our calculation. And that, I feel this is a little bit easier. Start with your number, take the biggest values out, put 1s in that column, subtract it, and continue on. Okay, so we've done a binary conversion where we started with a decimal number, we ended with a binary number. We're going to do this the opposite way. I have my chart here, I have my paradox numbers to the values, I have my positional values of the columns all written down, so I have my 8 columns, I have that here. What I'm going to do is I'm going to take the number 010110001 and figure out what that, from binary, what that number is in decimal. I have my chart. What I'm going to do is put that number up in the chart, and that gives me values and positional values, and now all I have to do is calculate that out. As I look here, once again, 0 times a number is 0. I'm not going to put that on my list, so I won't put 0 times 28, but I will put 1 times 64 on my list. That gives me 64. 0 times 32 is 0, so I'm not going to put that in my calculations, but I do have a 1 in the 16 column, so I'll put that in my calculations. 1 times 16 is 16. I also have a 1 in the 8th column. I'm going to put that in my calculations. 1 times 8 equals 8. There's a 0 in the 4 column. 0 times 4 doesn't affect my number. I'm not going to put that in my calculations. Same thing with 0 times the positional value of 2. That equals 0. I'm not going to put that in my calculation. But I do have a 1 in the ones column. I will put that in my calculation. Down here, that gives me 1 times 1. Now, since I have my values, all I have to do is add this up. 64 plus 16 plus 8 plus 1. Add those together, and that gives me a value of 89. And what we just calculated was binary number 010110001. That was what we were given right here. We now went through and calculated the decimal value by multiplying the number times the positional value, and that gave us our 89. We took a binary number and converted it into decimal. Now, what does this all mean? This means we can now start to understand a little bit about IP addresses. We can start to understand how these IP addresses are seen by computers and devices on your network. An IP address is 32 bits long. The computer sees this down here as an IP address. It's not broken up in groups of 8, so it's one constant string of ones and zeros. A binary number, just ones and zeros. That's how it is. But for us humans, we take and we break it up into octets. We take 8 bits here. 8 bits are called a byte, and we divide it up here. We divide it there. We put the decimal point in there. We put another division here. Put a decimal point. We divide it up here. We put another decimal point in there. To make it even easier for us, what we do then is take this 1 byte of information. 8 bits equals 1 byte, so we take this 1 byte of information, take the binary of that, and then convert that into decimal. When you convert 11000000 into binary, that's 128 plus 64. 128 plus 64 gives us 92. This is done only for humans to more easily understand that. Computers, they don't see this. They see this string of 32 ones and zeros. This is the big takeaway here. Yes, you have to know how to convert binary to decimal and decimal to binary, but also understand computers sees an IP version 4 address as a string of 32 ones and zeros. Nothing breaking it up. There's no octets. There's no decimal points. It was my pleasure to provide you with this wonderful episode on binary number systems. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com. And you can get all of these episodes in video and podcast form. In the upper right is my playlist for my series on Introduction to Networks. In the bottom right is one of my favorite videos that I picked just for you. Thank you so much for watching this episode of my series on Introduction to Networks. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.